Hey guys, what's up? I hope you're all doing well. I hope my love Christ is with you. And this is called How to Do Math in Your Sleep. No, that's not like me being braggadocious. It's more like I literally haven't slept, but got me some coffee and thought, oh yeah, I'll do math. Because like someone told me that like they like hardworking people. I'll be as vague as possible, and so I'm about to go ham. No, really, like I was always hardworking, but yeah, I might just go ham. Okay, all right. So in this video, we're going to talk about what a basis is, and it's like one of my favorite little things, right? I've always wanted to make a video on it, and here we are. So yes, it's an English word, but we're talking linear algebra, right? So a basis is a linearly independent, I'll break this down, linearly independent spanning set for a particular vector space. Right? Okay. So first of all, what does a spanning set mean? Let's start there. So a spanning set is a set that generates the entire vector space, right? And the other question is, what does it mean to be linearly independent? Being linearly independent means that like the only way to get to the zero vector in that vector space is by using coefficients that are all zero, right? So, like, I'll give you an example, and these ideas will become more concrete. For example, if we take the field R3, right? So that's just like a triple order pair. So order pair is no. What do you call like 3 coordinates? An order pair is just an x, y, right? And so 3 coordinates. I used to know this. I'm getting old, people. It's x, y, z, right? Anyway, for so in R3, we're looking at like an x, y, z triple, right? Okay, and so like you know, basis for R3 is the set. So in R3, a basis, and this is not the only basis. This is a standard basis. So a basis in R3 is the set E1, comma E2, comma E3. This is called the standard basis. As I said, as I just got done saying, this is not the only basis in R3, and so like vector space can have more than one basis, right? Okay, so E1, E2, and E3, if you don't know what they are like E1 is 1, comma 0, comma 0. E2 is 0, comma 1, comma 0. And E3 is, that's an E. E3 is 0, comma 0, comma 1. So you should be able to guess that in your sleep after I show you the first one. Okay, so this is both linearly independent and a spanning set of R3, and therefore it forms a basis for R3. So how in the world is this linearly independent? Well, let's show. Shoot. Alright, I bought this one myself. My mom didn't buy this, I bought it. She would never buy me something this crazy. Okay, anyway, so let's show that it's linearly independent. What I said for linear independence is the only way to get to the zero vector as a linear combination of these sets, right, would be by using coefficients that are all zero. So, like, you know, let's say we have some constant A1 that we multiply E1 with. So then this is what we're looking at. And then linear combination means like adding and subtracting, right? So obviously, like, you know, I'm using plus because like the second constant, this may be negative, and so that might be a minus. And so again, it's consistent with like the definition I offered on linear independence, linear combination, meaning adding and subtracting. So A2 times, it's 0, 1, 0, right? plus A3 times 0, 0, 1, right? And so we want to get to 0, 0, 0 from this, right? Well, the only way that you could combine these and get to 0, 0, 0 is if A1 is 0, A2 is 0, and A3 is 0. So we just showed then that E1, E2, and E3 are linearly independent. Another way to say linearly independent is that like none of these three vectors in R3 can be made of the other two by like using coefficients and combining them, you know, via addition or subtraction, which again is called linear combination, right? So in other words, like I could not create this vector in R3 by like multiplying this by a constant and then multiplying this by a constant and combining them. And I could say the same about this one and this one. And that should be very abundantly clear, right? So that's linear independence. So then what is spanning? Spanning, like again, the lay word for it, like the easier word for it, is generating, right? So spanning is like generating, right? So we're saying that these three generate every vector in R3. For example, if XYZ is like -3, this is almost trivial. -3 and then -12 and comma, let's say that like I don't know, 7, then obviously this vector is made of -3 times E1 plus -12 times E2 plus 7 times E3, right? Because, well, if I did this, -3 times E1, that will change the first coordinate from 1 to -3, and the -12 there will change the second coordinate, like in E2, right? Because I'm multiplying E2 there, and you get it. Yeah, okay, that's what a basis is. And I really like not just the word, but like what this encapsulates a basis. And I'll give you more sophisticated examples on a basis for example, polynomials and such. I have videos on them. In fact, I have a video in numerical methods in my numerical methods section on how to generate like polynomial basis. So check that out if you'd like. But otherwise, I hope you enjoyed this, yeah? And have a great, have a great day. Like, so this channel, Truth Unedited, which is all about Christ, he claims that this too is like that okay symbol that like is like, you know, from the enemy. And I'm going to trust him because he's a good teacher. And so I'm no longer going to do this. I'm just going to do this because this works. Yeah? Okay, have a good one.